Hello everyone. Now today I'm going to be talking about why you should consider WebAssembly in your next front-end project. My name is Håkan Silfvernagel. I work with machine learning and AI at Miles. And before we dive into WebAssembly, I'm just going to give you some more background information about me. So my background is in human-machine interfaces for process automation and robotics. I have a master's degree in electrical engineering and also a master's degree in behavioral science. I'm also interested in artificial intelligence and Internet of Things. So I've taken some classes at MIT, and I am a Microsoft MVP in AI. And I'm also part of the steering group for two meetups here in Oslo AI and the Norwegian.net user group. So what is WebAssembly? So WebAssembly has its origin in 2015. So all the major web browser vendors, they gathered together and they did a draft of WebAssembly in the end of 2017, and then they published it in February of 2018. So the goal here for WebAssembly is to have like a binary format so that you can run native code inside of your browser. So in this presentation, we will both have a look at WebAssembly, how you can write it, and we will also have a small demo of how you can write your own WebAssembly, and then how you can package it with NPM, and then how you can then download the NPM package and use it in your own web application. First, if we contrast JavaScript and WebAssembly, we can see that JavaScript is more of a high-level language. It's flexible, expressive, dynamically typed, and you don't need to compile, and also it has a huge ecosystem. Whereas WebAssembly is much more low-level, and we will see in a couple of slides, we will see what it looks like, but it looks like an assembly-like language. And it also has a compact binary format. And one of the advantages with using WebAssembly is that you can have near-native performance. So either you can write WebAssembly manually, which I don't recommend, or you can use a high-level language like C or C++ or Rust and Go, and then you can use a tool or a compiler to compile down your high-level language to WebAssembly. So this is an illustration. This is taken from a blog series by Lynn Clark. So you will get all of the references at the end of the presentation. But basically what this illustrates is that what usually happens is that you have a high-level language like C or C++, and then you compile this high-level language down to something you can call an intermediate representation. And then you have a second part of the compiler will actually compile it down to the target architecture, which is in this illustration can either be an x86 architecture or an ARM architecture. But now with WebAssembly, it's a little bit different because now here we have code that will be executed over the web. So that means that we don't really know which target architecture will it run on finally. So WebAssembly can be described as a machine language for a conceptual machine. And these WebAssembly instructions are also called virtual instructions. So what will happen is that the browser will download WebAssembly, and then it can compile down to the target that it's running on. As I said before here, so WebAssembly, which is abbreviated WASM, is a new browser standard. It is based on a previous project called asm.js, which you can read up on more. And it's an intermediate language in the same way as Java compiles down to bytecode and C# compiles to MSIL. It's a strongly typed language, but we only have 4 different types. We have integer 32, integer 64, and float 32 and float 64. If we take a look here at the Hello World program or Hello Wasm program, since I just mentioned that we only have 4 different types of types in this language, and they were integers and float, it's a little bit complicated to actually write a Hello World program. So instead, what is the equivalence of a Hello World program in WASM land is either an addition or a subtraction or some more simple mathematical operation. So we will make our own add as a Hello World program in WASM.
So WebAssembly has a format which is called WAT, which stands for WebAssembly Text Format. So this is how we can write our WebAssembly code. So what we have here is we define a function called add2, and we define two input parameters, which is integer 32. And then we also declare that the result from this operation should also be an integer 32. And it's also a stack-based language. So here we get local on the first memory position and get local the second memory position. And then we call a function here, i32 add. So there are some 60 different types of functions that you can use in WebAssembly. And then we also have to declare what will this function actually be called for, for the calling function. So we export it as a function name that should be add2, and this add2 is an alias for the function that is called add2 here in the WAT example. We can use a tool here which is called WAT to WASM, or WebAssembly Text Format to WASM. So we just run this is a command line based tool. So we run WAT to WASM with our WebAssembly text format, and then we define what kind of format we want to have as an output. And in this case, it's an object format or a binary format, so it will be to the add.wasm. And we can also have a look at what this looks like in what our binary format will actually looks like. And then you can see here on the slide that this looks very much like an assembly language. But how do we do now if we want to use our WebAssembly that we have built? So the first thing is that we need to fetch the WASM file, and then we can read it into an array buffer. And then after that, we can use WebAssembly, since WebAssembly is a standard. So it's supported in all major browsers. We can call WebAssembly.instantiate with this bytes array that we just read in. And then from the results of this, we can take the results.instant.export. And then here we declare the function name that we declared in our WebAssembly called add2. So we assign this to a JavaScript object add2, and then we can just run it as a regular JavaScript object. So we just to see what it looks like, we can just make alert and then add 2 of 2 integers. So then we will have, we have made our first Hello World program in WASM. So another tool which can be interesting to have a look at is something called the WASM Code Explorer. So with the WASM Code Explorer, you can load a binary WASM file into the WASM Code Explorer, and then you can have a look at the text format of that file. So here we have actually taken the binary file that we downloaded, and then we have uploaded into the WASM Code Explorer. And then you can see here on the right-hand side in this tool that we get the same textual representation as what we actually added in the first place. But this is quite cumbersome to write WebAssembly by hand, so that's not really recommended. So instead, what I said was that what we would like to do is we would like to use a high-level language like C or C++ or Rust or Go, and then we would like to compile this down to WebAssembly. So now I'm going to show you how we can do this using Rust. And before we do that, we have to have just a quick introduction to what Rust is. So Rust is a system programming language from Mozilla. So it has a syntax similar to C or C++. It's strongly typed and it's compiled down to native code. And one of the design goals with Rust as a language is that it should be memory safe guarantee. And that's a very huge benefit with using Rust. Now when we use Rust, we need to be aware of the tool chain here. So the tool chain basically consists of 3 different tools. So first up is RustUp. That's an installer for Rust. And then we have something called Cargo, which is the Rust package manager. So there is there's a compilation of different crates. So you can have a look at crates.io. That is sort of the package registry for the Rust community. And then we have Rust C or Rust compiler. So that's the compiler for Rust. If we make a hello world program here, we can define a function and it should print out the hello world. And then we can just run Rust compile with the main.rust. And then on Windows, it will generate an exe file. And then it will just execute our Rust code. We can also use cargo if we also in the command line, if we write cargo new and then the name of a project, it will create a binary application and the project. So you will get a source folder containing a Rust file, a main Rust file, and you will also have a package declaration, which is called a TOML. So in our main Rust file, we have a definition for a main function, and then it will just print out the hello world. And then in the TOML file, we have the package definition where we need to define the name of our package, a version name, and also the authors. And if we have some dependencies on some other crates, we can define that also here in the package definition. We can use cargo to run this. So we just run cargo run, then it will compile our project, and then we also run the exe file that will be generated, and then we can see the result of it in our command line window. So with Rust, we also have some types here. So we have primitive types, we have Boolean, integer, and float, and text. We also have some primitive constructs like tuples and arrays, function pointers, and so on. So now when we know a little bit more about Rust, now we'll look at how can we use Rust to generate a WebAssembly file and then publish it up to NPM. So the first thing that we need to find out is how can we compile Rust down to WebAssembly. So the first step in order to do that is to install this Rust toolchain that I was just talking about. And then we need to add a new compile target, which is called wasm32 unknown. So with that target, then the Rust compiler knows how to compile it down to WebAssembly. And then we also need to install something called a bindgen, wasm bindgen. So wasm bindgen, what it provides for us is that provides bindings from the application JavaScript code to Rust and to Wasm, so that you actually can call your file from your JavaScript code. This is an example here. So here we have the package definition. So we call it the Hello Wasp. Silver is the name of our package, and we define some version and the description. And then we define what kind of library is this. So then we have something called the C dynamic library, which we put under crate type. And then we also need to find some dependencies. So one of the dependencies is this tool that I was talking about, the wasm bindgen. And what it actually does, it generates some glue file that we will have a look at. And this is our Rust main file here. So we need to define that we have dependency on an external crate. In this case, it's the wasm bindgen, and then that we want to use also the wasm bindgen. And then after that, we can define an external function, an external JavaScript function that we want to use. So we want to be able to use the JavaScript function alert in order to print out something here. And then we can define our function, which is a public function that the calling application will be able to use. So we name our function greet, and it has a string input parameters. And then we just use the standard alert function in order to print this out on the screen. So if we then want to be able to package this so that we can load this up onto NPM, then we can run a command here called wasmpack init. So what that will generate, it will generate a package folder with this content, and then we can just publish it just as we would publish any other regular NPM package. We can just do the NPM publish package. And then as you see here, then the result is that on NPM we have a package that someone else can use to in order to add it to their own application. So we'll have a quick look here at what has been generated into our package folder. So you can see here that there are 4 different files. The first file is a TypeScript file. So in this TypeScript file, it's declared what is the different types of functions that we will be able to call from JavaScript. So here we can see that there is a greet function that we will be able to call, and we can also see what is the format of our input parameter and what will the output be. And then it also generates something that we can call a glue file. So that is hello-wasm-silver.js. So this is a JavaScript file that you can call from with your own JavaScript application code. And this glue code will then call into the WebAssembly. So you can see, for example, for the function greet, it will try to pass a string down to Wasm, and it will take the input parameter that we defined. And then it will try to call this return wasm.greet, which is the function that we defined in the Wasm code. And then after that, we have to free up our memory. And then we also had the package.json file, and that's just a regular package.json file where we define what kind of files we have. We have this TypeScript file, and we also have this glue file that I was just talking about. And this is then how we can use this in our web application. So we can define a webpack config, and we can define a package.json for our web application. And in this package, we just define that we have a dependency on our hello wasm silver package. And then we can just create a regular index file. And we point this, we are using an index.js file where we can bootstrap our Wasm Silver package. We call this asynchronously with JS, and then JS greet, and then whatever we want to have output on the website. And then this is the result from that. This has been sort of an introduction or a simple example of how you can use Rust in order to compile down to a WebAssembly, and then how we can use npm to package this WebAssembly and upload it to npm, and then how we can use the npm package in our own web application. I'm going to show you a little bit more complicated application here where we have some more input. So this is an application which is an implementation of Game of Life. So for those of you who do not know Game of Life, it is a simulation. So you have some rules for your simulation that if you have a live cell with fewer than 2 live neighbors, it will die because it's underpopulated. Or if you have a live cell with 2 or 3 live neighbors, it will live on to the next generation of our simulation. Or if you have a live cell with more than 3 live neighbors, it will die because then it will be overpopulated. And any dead cell with exactly 3 live neighbors will become a new live cell because of reproduction. And you can have a look at this example more on the link below here. This is what it looks like. Here we can see that the simulation has started, and then we can use our pause button like this, and then we can go in and edit manually inside our simulation. So now we added some new cells in the simulation, and then we can continue running our simulation. This is written in WebAssembly, and we're going to have a look at how this is done. Again, here is our package, our cargo package definition. So we define the name, the Wasm Game of Life, and the author and the version. And we need to define what type of library is this. So this is this C dynamic library. And then we also need to define our dependencies. So we need to, as before, we need to have dependency on this Wasm bindgen in order to generate this glue code that I was talking about. Then this is an extract of the actual Rust code that we're using. So here we define sort of the game plan or the universe. So we define the width and the height, and we also define some accessor functions for the width and the height, and we also define a function here in order to be able to toggle our cell. So this is our TypeScript file where we define what kind of functions exist and what can we call from the outside world. So you can see here that we can call our width and height, and we can call the number of cells, and we can also call our toggle cell function. This is this JavaScript glue file that I was talking about. So again here we have example for the width. It tries to call the wasm.universe.width in order to retrieve what is the width of this simulation plan. And we also have the toggle cell function, which takes some arguments in the x and y coordinates for the cell that should be toggled, and it tries to call down to the wasm.universe toggle cell function. Then here in the HTML code, we can just define a bootstrap JavaScript file where we can load our WebAssembly. And then we can just import this universe that we defined in our package. And for example, over here, we have just highlighted that you can also call your universe.toggle cell here from your JavaScript file. So now some questions here about performance, because what I said in my introduction was that one of the benefits of using WebAssembly is that you will be able to run near native performance. We're gonna have a quick comparison here between if you run WebAssembly or if you run JavaScript in 3 common browsers, in Chrome and in Firefox and in Safari. So they have run the same type of simulation using both JavaScript and WebAssembly, and as you can see, WebAssembly is quite a lot both faster than the JavaScript, but what maybe is even more important is that it has a constant spread, so that if you run WebAssembly, you can be more certain of what type of performance you will be able to achieve. Whereas, for example, you can see in the middle one, the JavaScript on Firefox has quite a large spread of the different trials. So then you don't actually really know what type of performance you will actually get in the end. We should also take into account that WebAssembly is still quite a new language, whereas JavaScript has been with us for a lot of times, where we had much more time in order to optimize the JavaScript compiler and the JavaScript runtime. So we can expect that these differences will be even more will be even higher in the future. And I also have some examples here from how WebAssembly has been used in real-world applications. My first example here is for a digital signal processing library. So one big benefit of WebAssembly is that you can use, if you have already a library which is written in any of these languages that I mentioned, like C or C++, or Go or Rust, and you want to webify it so that you can use it over the web, then WebAssembly is a great tool in order to do that. Here's an example of some people, they already had a C library with some transformations for image transformations and video transforms. It's called WebDSP. And then they used WebAssembly in order to be able to run this on the web. This is an example of what this looks like. So this is in real time, where we can change our video transform, and then it just runs through WebAssembly and then down to the C code, and and you can have this real-time transformation of your images and of your videos. So the benefit of this is that you already have some application code that you are already using and that you can trust, and then it's a small step to just use WebAssembly in order to be able to call this through the browser. Another example of this is AutoCAD. So for those of you who do not know, AutoCAD is a company that deals with drawings of constructions and buildings and so on. So so they have a huge amount of drawings going back to both the 70s and the 80s that they still need to somehow be able to provide to their customers. So in 2010 they tried the latest technology at that time, which was a Flash app. So to do a viewer for AutoCAD, viewer using Flash. And if we fast forward to 2014, then it was the HTML5 JavaScript was trending at that time. So then they made another viewer application using that. And then in 2016, they used a compiler called mscripten to be able to compile C++ down to JavaScript. And then in 2017, they used something called RealDWG, which is their own format for these drawings. They made a viewer for that, which is web-based. And then in 2018, they made an AutoCAD web app using WebAssembly. So the interesting thing with this is how this application has been structured. So basically, you have on top some normal web technologies like React and TypeScript, and then you have UI. You can have UI component libraries, and then you have this WebAssembly binary, and this will call down to the AutoCAD core library, which is this C++ code. So that means instead of having to rewrite their whole portfolio of code, they could instead just use WebAssembly and reuse their existing native C++ libraries and expose this as a web application. I'm going to be talking about some future plans here for WebAssembly. So one thing that I've mentioned in my talk here is that we have some JavaScript glue file, which acts like a sort of intermediary between your application code and WebAssembly. So, but that's not very performant. So what they would like to try to do is would like us to be able to call directly to the DOM or directly to a web API, and not having to be restricted to this glue file that I was talking about. And in the same thing, we would also like to just be able to do an import of Wasm in JavaScript. So also as maybe you saw here in my previous examples, I had to load my JavaScript asynchronously in order to be able to run it, but they would just want to be able to import it just as any other type of library. And then in addition, they would like to support more languages. So so as of now, it's one of the criteria for a language to be able to compile down to your WebAssembly is that you can't have a garbage collector. So for example, Java is not supported as of now. Another new thing here is called Serverless WebAssembly. So WebAssembly is not only for the browser. We have some different providers like Cloudflare and Fastly that can support WebAssembly, so that you can actually write your serverless function in WebAssembly. So why would you want to do that? One of the things is that you will have much faster launch time, and you don't need to rewrite. Maybe you already have some server code, and you can just use WebAssembly instead of rewriting it to JavaScript. So this is an illustration of the different types of options that we have. Either we can have WebAssembly running on the back end, and we call WebAssembly from the front end. We can have client-side JavaScript, or we can have client-side WebAssembly, or we can have this serverless WebAssembly that I was just talking about. We have also something called WASI, or WebAssembly System Interface. So one of the ideas with this initiative is that they want to be able to run WebAssembly outside of the browser. So to make it less restricted so that you can actually run it in different environments. But then we need to have an interface for this, a conceptual operating system that could interoperate with this WASI standard. And the goal for this is that you should be able to run WebAssembly on all types of operating systems. So as of now, when you run WebAssembly in the browser, it needs to adhere to the same type of safety restrictions as JavaScript. So there are lots of things that you can't do with WebAssembly. But if this WASI standard comes into place, then you can have some sort of intermediary that can negotiate with the operating system and see if is this file okay to be run, and if it is, it will just transfer the file over to the operating system. Now, finally, I'm going to talk a little bit about some other frameworks here for that is using WebAssembly. So one of this frameworks is called AssemblyScript. So AssemblyScript compiles a subset of TypeScript down to WebAssembly using a compiler called Binary. And you can see here an example of how that looks like. And one of the things that you need to be aware of if you run AssemblyScript is that you need to handle the memory allocation. So you both need to allocate some memory before you start to use your AssemblyScript, and then you also need to free your memory when you're done using it. And we also have Blazor. I know there are several talks at this conference that talks about Blazor, so I'll just mention this very, very briefly. Basically, Blazor is a framework where you can write your web applications just using regular C#. So it has there are two types of flavors of Blazor. Either you can run it on the server, and then you have client events that is sent back using Signal R, or you can run it on WebAssembly. So then you will actually have a version of the .NET framework running on WebAssembly. One important question here is, isn't this just the new, old, new, old, new? Haven't we just seen all of this before? We take some examples from the past. We had ActiveX, and we also had Flash, and we had Silverlight, and none of these were has survived. So why would WebAssembly have a higher chance of success than these previous frameworks? And so for once, all of these were proprietary to the company that was making these toolkits, whereas WebAssembly is a standard that has been agreed upon between the different browser vendors. So there is a much higher probability that this will be something that we can make use of a long time in the future. So what is the conclusion of all of this? Because when I first started to hear about WebAssembly, one of the headlines was that JavaScript is dead and long live WebAssembly. So the question is here, should we do WASM all the things? Well, I don't necessarily think that. I think that WebAssembly is just one other tool in your toolbox, and it's one of the use cases where it really shines is if you already have a set library of either C or C++ code, and you want to be able to expose this out in the browser, and you don't want to rewrite your whole library, then WebAssembly is a really great candidate for that. But another thing that we also need to be aware of is that we're still sort of in an early phase. So there's a
there's a lot of tooling that can be improved because quite frankly, some of these tools are a little bit clunky to use right now and it's not super user-friendly. But I think that this will also change with time. So to finish my presentation, I will also give you some references with some articles where you can read up more on WebAssembly, and you can also read a little bit more about Blazor if you're interested into that. With that, I hope that you find this inspiring and that you would like to find out more about WebAssembly. And if you want to reach me, you can reach me either on Twitter or you can send me an email. And I will be here throughout this remaining 3 days on the conference. I'll be both on the Slack channel. So if you have still have some time left here for questions, so you can write the questions either in the Q&A panel here on WebEx, or you can write some questions on Slack. With that, I would like to thank you all for your time. Thank you so much.